Hello, I'm Juliette Achddou, and I'll be talking about efficient algorithms for stochastic second price auctions. This is a joint work with Olivier Cappé and Aurélien Garivier. So second price auctions are a bidding mechanism in which a set of bidders submit their bids to get an item at sale. The highest bidder wins, but she only pays the second highest price, as on the figure here. Second price auctions possess the important property of being truthful, which means that when you know the value the item yields, the optimal strategy is to bid this value. This is one of the reasons why they have long stayed the predominant mechanism in the field of programmatic advertising. Even though they have been largely replaced by first price auctions in this field, second price auctions are still an interesting model for the main system in programmatic advertising, that is, real-time bidding. In this framework, very similar items are sold repeatedly. These items are placements on a web page visited by similar users. The value the advertisers attribute to these placements are materialized by a click or a purchase. These events can both be modeled by a Bernoulli distribution with a very low parameter. We are specifically interested in the following stochastic setting, where at each time step, the bidder has to submit a bid BT for the item that is of unknown value VT. VT is going to be drawn from a distribution on 0, 1 in an IID fashion. The other players on the side submit their bids, the maximum of which is called MT. MT is also going to be drawn from a distribution 0, 1 in an IID fashion. If MT is smaller than BT, that means that the bidder wins. The bidder observes and receives the value VT and pays the second highest price MT. Otherwise, the bidder loses the auction and does not observe the value, which is a form of censoring. And the goal is then to build a strategy so as to optimize the cumulative reward, or equivalently to minimize the cumulative regret. Here, the regret is the difference between T times the best utility and the expected effective utility, where the utility is defined by the expectation of the return, VT, which is what we receive, minus MT, which is what we pay, multiplied by the indicator of the events of a win of a one auction. In the following, we will be interested in bounding this regret, both with parametric bounds and worst case bounds. The framework that we are interested in is that of a censored continuous bandits, where there is a certain form of exploration-exploitation trade-off. In this setting, exploitation consists in bidding close to V because of the truthfulness of second price auctions, and exploitation consists in bidding high enough because, for example, bidding 1 means observing everything. So now let us consider a very simple example where MT is uniform, VT is drawn according to a Bernoulli of mean V. And in the setting, we see that the utility is quadratic around V, so that there are two values, for example, B1 and B2, leading to the same utility. We will always tend to prefer the highest bid B2 because f of B2, which corresponds to the ratio of observations, is larger than f of B1. So this is exactly the principle behind UCB algorithms for bidding in second price auctions. So these algorithms build an upper confidence bound for the value. The first one, UCB, had already been studied in a previous work and is based on Hoeffding's inequality. KL UCB and Bernstein UCB are refined algorithms that rely on tighter confidence bounds that take the variance into account. We provide an upper bound of the regret for all three algorithms. All three grow with the horizon with a log squared t behavior. The parametric dependence, however, differs greatly. The first bound for UCB relates to the ratio of observations under the optimal policy, 1 over f of v, while the two others compensate this factor with a variance term. This is in particular important when v is small. This parametric dependence can be shown to be about optimal when the values are drawn according to a Bernoulli distribution. And among strategy that bid higher than v with a high probability, which is the assumption in blue. A reasonable question is whether this assumption is necessary to achieve good performances. This is one of the reasons why we choose to study simpler strategies that are reminiscent of explore then commit strategies for traditional bandits. Another reason is that obviously the simplicity of strategies is critical in real-time bidding, where everything needs to happen in a real-time fashion. The explore then greedy algorithms proceed in two phases. So in the exploration phase, we choose to bid 1 to force observation. Then the bidder chooses either to continue with a running average of observed values, that is the greedy phase, after a well-chosen stopping time, or to completely abandon the bids, that is to bid always 0 after another well-chosen stopping time. The choice of tau 0 that we see here enables to guarantee that the exploration phase, does not last too long if the value is really small, while tau 1 guarantees that we don't underestimate the value by a factor larger than 2 in the second phase. We provide a regret upper bound for explore then greedy that shows that for a small value, the regret can go up to t to the power of 1/3, while when v is large compared to t to the power of minus 1/3, the regret is of the order of log squared t, with a parametric dependence of the form of 1 over f of half of v. We have also done various simulations with value distributed as Bernoullis and uniform MTs. On this plot, we see that even though the asymptotic regret of Bernstein UCB is smaller than that of UCB, it is in reality larger in the first time steps. It also shows that KL UCB outperforms UCB. Next, we have plotted the regret of all studied strategies at the end of an experiment of horizon 10,000 against the average value v. As explained, we show that explore then greedy is now well behaved around v equal t to the power of minus 1/3. The worst case for UCB seems to be around the value 0, while for KL UCB and Bernstein UCB, it seems to be somewhere at the center of 0,1. Explore then greedy outperforms even KL UCB when v is large enough. To conclude, we have shown that UCB can be refined with tighter confidence bounds. The new algorithms that are developed with tighter confidence bounds show increased performances with respect to the parameters and dramatically better worst-case regrets, which is shown in the paper. A parametric lower bound shows that the parametric dependence of KL UCB is optimal among optimistic algorithms. Next, explore then greedy algorithms work well for a large class of problem instances which is when V is large enough, but cannot give as good a worst case regret as KL UCB. This is also proven in the paper. So thank you for listening.